All right. Good evening, everyone, and you are welcome to today's episode of data science demonstration. All right. So while I'm trying to share my screen, so on the WhatsApp group, we had a short. Okay. So I believe my screen is on now. So we had a short poll, and people who wanted SPSS one. All right, so but nobody um did not win. Nobody lose. It's just as much as we have we have like 9 people wanting SPSS and 6 people Python. Then maybe 1 or 2 for Excel and R and Starter and so on. So for today, we'll demonstrate with SPSS, and then either during the week um, or maybe next week next week Saturday, we would see how to do same with Python. All right, so I already have these are the Python codes, apart from visualization. So it's no it's no big deal, but because most people want SPSS, so start with SPSS today. All right, so that being said, I believe you're not new here. For those who are new, this is Quiver Analytics, and this is why we are here. You know, we are trying to have fun with data, and we'll be working with a fictitious data. I prepared the data. This is the data. I will call it Kwams on a plane. All right. So, predicting disruptive trends. Unfortunately, for today, we will not predict anything. We will just understand the pattern. All right. When we get to Python, Python is more flexible and will predict. We can predict things. All right. So we have a WhatsApp group that you can always join for updates because things get to the WhatsApp group um, the the main group. Now, something coming up very soon is the data science internship. Starting September 1st, we have over 100 data science case studies that will explore starting from September. And it's self-paced, so if you can explore, and there are exams, tests to check your knowledge. So if you can explore all of them, fantastic. It makes you, and the fun part of it is you can do most of it using SPSS, Python, R, Starter, and then some that are supposed to be done with SQL, Power BI, they will be stated. All right. So without wasting more of our time, we go straight to what we have the business for today. All right. So, okay, I think let me. It's better for me to just put off my video so that to help people's network. Boy, boy. All right. Okay. So, Kwams on a plane, data science modeling, predicting chaotic passenger behavior with logistic regression. Last week we talked about a regression, and it was the multiple linear regression. We call this the OLS regression. That's the one everybody knows. There are different types and families of regression. This is logistic regression. It is um, people in health and social sciences, they are much more familiar with it than business people. Yeah, it should be. Yeah. Let me just say that. All right. So now we have about the data sets. Okay, let me talk about logistic regression just for a minute. Last week we predicted a scale variable, numbers. We did a model that can predict numbers. This time around, we are looking at a model that can predict events, and we are focusing on two events. We call it bivariates. We can uh, predict whether someone is chaotic or not chaotic. So the chaotic people, we call them Kwams. You know, it's while I was preparing this, I realized that Kwam actually means trouble or chaos. So then we have no Kwams. You know, in Nigeria, when we want to say no wahala, we just say no Kwams. All right. So the non-chaotic people are the no non-chaotic. I mean, they are the no Kwams people. So we want to know who are the people, the set of people that their pattern would likely cause chaos on the airplane, and those who would not likely cause chaos. Now we have a data set with 120 airline passengers. So we already know these people. These people have flown before. We've collected this data from an airline. Remember, I said it's fictitious. I made the data. All right. So, but we are assuming now that we have collected this data on 120 airline passengers. Some of them have flown before, some of them are not. This is the data. I would magnify. All right. Then filter. All right. So we have passenger ID, just probably their seat number, and then we have the Kwam status. There are two possible outcomes that a passenger can be. A passenger can be a Kwams or a no Kwams passenger. All right. Then we have data on whether a passenger has short fuse or not. So those without short fuse, no, you can see we have 94 of them, and then we have yes 26. Those who have flown before, no or yes. Then the age group, we have income level, and they are high, low, middle. Then education, we have postgrad, secondary, tertiary. Then seat class, business, economy, and premium. Of course, we have the economy 72 and so on. So we'll still explore this in the data just to show you that we have characteristics. We call them attributes. We also call them independent variables. So from column C to column N are the characteristics of each passenger. And then their classification is already there. You know, this 120 people have flown successfully with the airline. Some of them repeatedly, some of them just once. All right. So, and then we know the ones that have been chaotic and the ones that are not. So now, if we have new data, we want to be able to know. If we have new passenger, we want to be able to know that is this person chaotic or not? Will this person cause trouble or not? So if the person is a chaotic person, that will say that, oh, the cabin crew should take notes, you know, handle the person professionally to prevent stories that touch, and 500 billion law cases. All right, so I'm talking a lot. I want to be fast and go into the data analytics proper. So we have the aims and objectives. You can read this at home at your leisure. And what we want to do is we want to explore the data. We want to do a contingency analysis with chi-square, and then we want to do logistic regression. This is where we are going. All right. So these are the workflow for predicting this kind of data sets. You can see we really don't have numbers here. We only have categories. Some those who are high, low, middle. We have age groups that are categories that are yes and no, and you know, Kwams and no Kwams, flying solo. They are categories. So this kind of data, how do we work with it? So the first thing we do is we convert it to numbers. So it's the same data that I've converted to number here. And like I said, you know, this is not a teaching class, it's just to show you how things are done. So I converted them to numbers, and it's pretty simple. No Kwams are okay, no Kwams 0, while the Kwams, number 9 Kwams, number 9 here, okay, so this should be number 10. Here we have 1. So no Kwams 0 and Kwams 1. All right, so that's I've transformed the data. Then for the code book, okay, so this is the code book. We call it code book. Every time you are doing a transformation, for those who are familiar with SPSS, you have to keep your code book somewhere. So you can see this is Kwams status, 0 for no Kwams, 1 for Kwams. Then flown before, we have 0 for no, 1 for yes, and so on. So all of this should be in the Excel that I sent on the group. All right, so those are the ways I transformed this. It's really simple to do that in Excel. Just do Control H, you see find what and replace what. So you find no Kwams, replace it with 0. Find Kwams, replace it with 1. It's that simple in Excel. So let's go to SPSS without wasting time. All right, so I'll close this one. Now this is SPSS. Again, I have done the configuration in the variable view. You can see the categories here: 1 for 18 to 25, 2 to this, 8 for 60 and above. And for the Kwams status, we have 0 for no Kwams, 1 for Kwams. All right, so this is where we label it in SPSS. All right, then you can see the numbers. Last week we had scale variables. This time around there are no scale variables, they are just nominal. Whether something exists or not, whether someone is well, just let me borrow this English that does not exist, whether someone is quamatic or not. All right, so it's category, it's a category, so that's why it's nominal. All right, now this is ordinal because it's serial number. Number 10 is greater than number 5, and so on. All right, so now once you use all of these things, how do they, from here, from age group to if they've flown before, how do they associate, or how good are they in predicting whether someone is chaotic or not? So this is SPSS. SPSS, the advantage of SPSS is that you can have your numbers as values. You can also have them as text. So if I click this label, value label, you can see my text is back. All right, so it sees it as text and it also sees it as values, and that's a very good advantage for SPSS. Now when we get to Python, you would see the limitation of Python there, you know. All right, so yeah, so the first thing we do is to explore the data. Because we have categorical data all through, we can easily run analyze, descriptive statistics, frequencies, and I'll reset because I've done this before. So I'm picking all the categorical variables outside ID because it's serial number. All right, I'm leaving display frequency tables. If you remember last week, I said if you have scale variable, you don't run the frequencies for scale variable and categorical together because what is needed for both scenarios are different. So we don't need statistics for categorical variables, for nominal variables, but we need charts if you want. So we can use either bar charts or pie charts. I see bar charts as better explanatory than pie charts. So I'm using bar charts and then continue. Again, this video is going to be on YouTube, so don't worry about my speed. Just be observant. Then when you watch it again on YouTube, you would pick it better on YouTube. All right, so yeah, so we've selected the charts, and okay, so SPSS, we have the output view, and you can see the different charts for age group. We have the people of 26 to 40 years age group. We have them more here than every other age group. So followed by 18 to 25, then 41 to 60. You know, so using this alone, the airline would know their passengers more. They have more of middle-aged customers, and followed by younger customers, then seniors, and then more seniors. Right, so then income level, we have the middle class and lower class, the education, tertiary more than secondary and postgrad. Seat class, of course, economy, then business and premium, and so on. So you can explore all of them by yourself. So let's look at the chaotic ones. And here we have the Kwams and the no Kwams. Remember last week I said you can double click your charts and come here and give it the exact label, then close it, and then you have, so we have 70% no Kwams, 30% Kwams. So among the airline passengers, 30% of them are problematic. Now, why we do this is because when a new customer comes, we want to be able to know, given the attribute of the ones we have before. When a new customer comes, we want to know that this person falls within the category of the chaotic ones or not, so we know how to handle them. All right, so these are the frequencies for the graphs that we've seen, for the bar charts that we've seen. So that ticks off our first objective, which is to explore the distribution of social, demographic, and behavioral characteristics of passenger. Then the second one is to check to assess association between predictors and the chaotic behavior. So now the next thing we want to do is to check. We'll use graph and we'll also use formal statistics to check if each demographic variable, each attribute of the passenger is associated with being chaotic or not. So in academics we call it bivariate level, in nursing and medicine and so on. So this is just it's like a basic analysis to see what are the variables that are associated, that seem to be associated with chaotic behavior or not. All right, so to do that we use the chi-square analysis, and what it gives us is it gives us an analysis with p-value. It also gives us a chart, a group bar chart. So to go there, we still go back to our descriptive statistics and go to cross tabs. All right, so because I've done this before, I'm going to reset. Now I'm picking the last one, Kwams, the Kwam status. I want it to be the column header. Like every table this analysis is going to give me, I want the Kwam status to be at the top. So it should, for all of the tables, I want the Kwam status to be at the top. Then every other one should be the row header. So I'm picking all of them and bringing them to rows. Now I go to statistics and I tell it I want chi-square. It's not chi. Some people call it chi-square. It's not chi-square. It's chi-square. All right. So there are some other things I can do here, but to keep it simple, I continue. Then cells. Remember, we are keeping it simple. It is still row. Then, like I said, we want a group bar chart. It is also called clustered bar chart. So I tell it to give me clustered bar chart. For now, we are okay. All right. So we do okay, and you can see running cross tabs SPSS gives me a lot of results. So I'll go from the top and see what we have. Now remember that last week we talked about parametric and non-parametric tests. Now chi-square, yes, so because the type of data we have, they are categories, they are nominal data. All right, so there is no need to, we know that it's not a parametric problem, it is a non-parametric problem. All right, so those are big English, but because they are categories, they are levels, they are nominal, we are not looking for tests of normality and all of that. So chi-square is a non-parametric test that is established. Now even for a non-parametric test, we talked about p-value. The rule of thumb for analytics is that when your p-value is less than 0.05, you say the test is significant. That means whatever that test is testing, we are sure of it. Whatever the output is, we are sure of it, that when we perform this experiment 100 times, 95% of the time, it is going to be the same results or within the range. That is what the p-value measures. And when p-value is not less than 0.05, if it is greater than 0.05, just like we have here, 0.374, it's still okay. What it just means is that there is no, we can't, from given the data that we have, we can't establish a relationship between. So here we have age group. Looking at the cross tab, we can't establish a relationship between the age group and the Kwam status. So what this means is that whoever the age, like in whatever age. So let's see. Look at no Kwams here, and we have Kwams here. Among the 18 to 25 years old, there are 23 of them are no Kwams, while 12 of them are chaotic people. So all the age group have chaotic people among them, and their numbers are probably close together, no much difference between them. So we really can't say there is a pattern. There is no association between age group and chaotic people. So that means that the airline knows that whichever age a person is, the person can be chaotic. So that's just what it means, despite that the p-value is not significant. So it just means that we cannot establish a relationship between age group and Kwam status. All right. So then the clustered bar charts, here we have the age group. Blue is for no Kwams, red is for Kwamatic people. All right, you can see even SPSS understands problem. All right, so we have the group bar charts, which is fine. Income level and Kwam status, again the p-value. So again, for chi-square, it does not write p-value, it writes it as asymptotic significance. The p-value is also called significant value. So this is the this is how it writes the p-value. So again, we can't establish any association between them. So airline, stay alert. A person can be earning low, they can be middle earners, they can be high earners, they can still be chaotic. All right, so education level 2, no significant association. And seat class, whether a person is in first class or not, or economy, a person can still be chaotic, right? And travel purpose, whether a person is going for leisure or business or family emergencies, they can still be chaotic. And they delay experience. All right, so someone who experiences delay can be chaotic. So here, this is telling us that there's a relationship between having delay and being chaotic. However, from this table here, we really can't tell which of them is it. Those people who don't have delay that are probably going to cause the chaos, or people with moderate delay, or people with long delay. So if I'm going to look at it with my own eye, I know that among 10 of people with long delay, only 7 do not have, only 7 are chaotic. Among 10 of people who have long delay, 7 are chaotic. So I know that most likely it's these people that would be very chaotic among them. All right. Okay, someone saying my screen is not showing anymore. I guess that should be your network, but for because of you, I'm going to stop presentation, then start again. And start the presentation again. All right, so all right, but usually it's your network. So where was I? So we're saying that delay experiences, people who have delay experiences, and I am saying, according to my own human estimation, it should be people with long delay, because that's like 70% of them are chaotic. But looking at among moderates, 23 and 16 is more than half of 23, so they might not be, we know that more than half of them will not be chaotic. 51 and 13, 13 is less than, of course this is less than 70% of 51, so people with no delay are less chaotic too. All right, so now we will still prove this when we get to the logistic regression. So we know that there's a relationship between, you can note it somewhere, that the delay experiences and Kwams status, there's a significant association between them. If you note, you see that I interchangeably use relationship and association. They are the same thing. All right, so alcohol intake, surprisingly, no relationship. And group type, whether the person is flying solo or pair or family, we really can't establish an association between them and being chaotic. And baggage issue, people who have baggage issue, there's no significant association between having baggage issue and Kwams. While connecting type, those who have connecting flights, there are some who have two, there are some who have one stop and direct. Again, we cannot establish any association between them. Then people who have short fuse, they are very, 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 very chaotic. All right, they are very, very chaotic. So among, you can see those who said yes. Total of people who said yes is 26, and among the 26, 22 of them gave the airline problem. So if there's a way the airline can check whether someone gets angry easily, then they would know that this person, probably while they are still in the waiting section, they look at how they behave. Someone who have displayed something for someone, blah blah blah, for whatever reason. All right, so those who have flown before, there is no significant relationship between whether they've flown before or displaying chaotic attributes. All right, so that's for chi-square. Remember, chi-square is not in depth, so it's just a surface view of whether a person, two relationships, two variables relate, or if they associate. And we've seen, I think, just two. We've seen short fuse and one other variables. That they are related with being chaotic. All right. So now for logistic regression, next is to do logistic regression, and in the logistic regression, we want to see if it also supports what we've done with chi-square. It has the ability to dig more deeper than what the chi-square does. All right, so I will go to, yep, okay, so now I go to analyze, and not descriptives anymore. I go to regression, and here binary logistics. All right, so it is binary because it is two, the outcome variable, the dependent variable. I explained dependent variable last week. Dependent, what we want to predict whether someone is chaotic or not. All right, so so that's why it's binary logistics. Okay, because I've done it before, I'm going to reset. So the dependent variable I said is the Kwams status. I move it to the dependent section. Then every other one, they are the independent variables. I move them here. Now that's not all. We go to categorical and move all the categorical variables here, and we leave it at default. So what this last means is that it says reference category. For logistic regression, age group, we have people from 18 to 25, 26 to 40, blah blah blah. So the last category, which is 60 and above, is the reference category, and we are telling it to use the last one as, yeah, we're telling it to use the last one as the reference category. All right, so I'm going to explain that again, then continue. And yeah, for now, that will be all. For now, we can do some other things, but the goal is to keep it simple, and it's just fine. All right, so we run the logistic regression. It's a little bit more complex than the linear regression that we did last week, but calm down, let me explain, like the online banker. All right, so the first thing we have here, it's peripherals of the model fitting. I'm not going to bore you with that. So we go to the last long table. So this is the last long table. We have block one method equals enter. That's the beginning of the last table. Now, from here, the SPSS starts evaluating the model. So I'm going to skip this. Where our reporting would start from is the model summary. Now, we have what the important thing we have here, the first table, is the Cox and Snell R². If you remember last week, we talked about the adjusted R². So the equivalent of the adjusted R² is the Cox and Snell R². And here it's telling us that 52, all these variables here, they are able to predict 52.0% of the independent variable. All right. Then the Nagel whatever NR² is telling us that they can actually predict 73.8% of the of the dependent variable. Like all these independent variables, the age, the seats, the class, the income level, everything joined together. According to this category, it says they are only able to predict 52%. The other category is saying they are only able to predict 73.8%. That's 0.73 times 100. Now, this table, the second table, is comparing. Okay, so the implication of this is that our model is good. If a model can predict 73.8%, that's very fine. Then even 52 is not bad as well. All right, so for the classification table, we call this confusion matrix, where we compare the observed value and the predicted value. So SPSS has done some predictions and it compares it with what it did was it fitted the model. They now use the data that we know to again make predictions. So SPSS now check that when the observed the original value for no quams, 77% of the time, it's correctly predicted no quams. You can see there's no quams here, no quams here, no quams and no quams. So 77% of the time it's predicted no quams when it was actually no quams. Then for quams, 26% of the time it's predicted quams when it was actually quams. Okay, it's not percent, it is just actual value. Sorry, it's actual value. That is 77 times, yeah, because if you add all of them together here, it should give you 120. So 77 times in 77 outcomes, it's predicted no quams, and our no quams altogether is just, so that means no quams was just wrong 7 times. Then quams was predicted correctly 26 times. All right, so on the average, the model is able to predict correctly 85.8% of the time. So if we have a model that predicts very well for 85.8%, then we are good to go. There is actually no model, well, let me not say, even ChatGPT, ChatGPT is a model. So ChatGPT does not predict something 100%. That's the reason why they call it confidence liar, hallucination. It's just as time goes by, it becomes better. All right, so we are rest assured that we will not be embarrassing people too much. Out of the 100 people that we are going to be managing very well, about 89 of them, 89 times will be correct, while like 11 times we may not be correct. 86 times will be correct, 14 times we may not be correct, which we will apologize. All right, so looking at the details of the outcome, so these are the details of the model. Now we have the age group, and the sig value is 0.5. Remember, the rule of thumb is that it has to be less than 0.05 for us to say that yes, age group can predict whether a person is chaotic or not. Now, I want to show you something at the beginning of this. So we have no quams 0, quams 1. So the tricky thing about logistic regression is that what you are interested in predicting. For this problem, the airline is interested in chaotic customers. So for a logistic regression, your quams, that thing you are interested in, should be the 1. It should be 1. If your no quams is 1 and your quams is 0, then you are predicting no quams. And these are the reasons why we have bad analytics out there and businesses make wrong decisions. Okay, someone is disturbing us. Please, can you mute yourself? Okay. Okay. So, someone is still. Okay. All right. So, I was saying that for a logistic regression, what you are interested in, the case you are interested to solve, should be your 1, and then it should always be 1 and 0 for the predicted variable. So we are interested in solving quams and no quams. No quams that we are not interested in should be coded as 0, while quams that we are not, that we are interested, we are not interested in no quams, so it should be 0. We're interested in quams, it should be 1. So that's what the model knows. Remember that your computer, your whatever, the model is not human being. There's no way it's going to know. Garbage in, garbage out. Whatever you give it is what to give back to you. So here we are predicting people who are chaotic, the quams. So age group is not sufficient to predict quams. It's not sufficient to predict whether someone is chaotic or not. All right. So which we've established that with chi-square. Income level. All right. So let me just explain what's this exponential b. The last column here is called the odds ratio. You might have heard that before, the odds ratio. And how we do that is, how we use it is that we say the age group 1. Remember, the first age group is between 18 to 25. So, and the last one is 60 plus. So we say that, we interpret this by saying that age group is 35.5% less likely to be chaotic than people who are 60 and above. Why 60 and above is because while we were fitting this model, we left it at default, which is to always reference the last category. So age group is 35.5% less likely to be chaotic than those who are 60 and above. Then the same thing for here, for the second one and the third one. While for any odds ratio that is greater than 1, we say that income level 1 for the low, level 1 is low, level 2 is medium, level 3 is high. So level 3 is our reference point. So we say income level 1 is two times more, like they are 2 times more capable of being chaotic than the high income. All right. However, we can't be sure of that because the sig value for income level is greater than 0.05. So we will not report this. So what we'll just tell the airline is that age group, income, which other one? Education, seat class, whether the person is in first class, middle, business class, or premium business class or economy, does not matter. Income level, education is also not significant. All of these ones are not significant until we get to delay experience. So all of these attributes of the airline passengers are not important predictors. So we'll tell the airline, don't look at their age group, don't look at their income, don't look at their education, don't look at their seats class. don't look at their travel purpose, but those ones that have delay, you have to look at them, you know. So among the delay, we have delay experience one. That this is those, you know, I was telling you about those with long queues, long delay. So here we say that the people who have long delay experience generally can be an indicator for a customer or a passenger that is going to be chaotic. So among the delay experience, look for the first one, like these guys, the long ones are more likely to predict to be more chaotic than the no delay. All right. Then, okay, that's for delay. Then for alcohol intake, also for chi-square, alcohol was not significant. Yeah, this is alcohol. Alcohol is not significant because it's 0.78. So this result still tallies with our chi-square value. Then for baggage issue, all right, so we have baggage issues 0.021. It is significance, and it is baggage issue 2 that is more likely to be significant, that predicts whether a passenger will be chaotic or not. So what's baggage issue 2? Let's go up and check. Baggage issue 2. Baggage issue. So the first one is none. The second one is overweight. So people who come into the plane with overweight baggages are most likely to be chaotic than others. Then those with connection flights, they are not going to, we don't have issues with them because it is not, according to this data, it is not significant. It might be something else for another airline, or you know, when we get more data, it can be something else for this particular airline as well. Then we have connect. Okay, so lastly, the short fuse, we have significance. So it means that those who have short fuse, like we've seen in chi-square, they can be, I mean, being someone with a passenger with short fuse is an indicator of someone who is going to be very, very chaotic. You know, you can see the sig value is almost 1. That's 0.0000. All right. So then those who have flown before, if someone has flown before, they are not likely to be chaotic. All right. So according to this model, according to this data, remember, it is not a real model. It is made. It is made up. And if we have a real model for logistic regression, there is no other way of doing it than this. All right. So that will be the end of today's class. You will get this file. I already dropped the SPSS file in the group. So every other file will be dropped, and when the video hits YouTube, you also get the link. All right. So thank you everyone for coming. We'll see you next week. Bye.